This is section 3.5, mathematical modeling and variation, which deals with, first off, two things that you've already seen before, direct variation and inverse variation. So in this video, I plan on talking about those. And then after that, we will talk about how to expand on that to other types of functions that maybe you haven't seen before, or other types of situations that are real life type situations. So direct variation. Y equals k times x. Direct variation is where basically if I take, for example, let's say, does anybody in here have a job? How much do you make per hour?
$7 to $8.
How much per hour?
$8.
$8 per hour? Okay, so if you're making $8 per hour, that means the function would basically be like your pay is equal to $8 for every hour that you work, all right? That should look a lot like this direct variation equation. So let's say that if I made an HP chart instead of an XY chart, if you work, how many hours do you normally get in a week?
15.
15 hours? Okay, that's easy to do. So 15 hours. So before they take out taxes and stuff like that, you would take 15 times 8. So that would be, what, 120? So roughly you get $120 a week before taxes if you get 15 hours per week. But let's say next week is like, I don't know where you work at, but let's say there's going to be a big rush of customers in there, and they're like, we need you here more than normal, and they suddenly double your hours. If you double your hours, what do you think happens to your pay? It doubles. So that just makes sense that it's going to double, right? What if they cut your hours in half? What if they only gave you 7.5 hours? If you cut your hours in half, then your pay would go down to 60. I don't even have to look at this part here because I know that this is a direct variation equation. And that's the way direct variation equations work. When you double your input, your output doubles. When you quadruple your input, your output quadruples. If you cut your input in half, your output gets cut in half, all right? Also, another characteristic is that if you don't work at all, if you work 0 hours, guess how much money you get? You get $0, right? So every direct variation equation goes through the point 0, 0. So its y-intercept is at the origin, all right? So a direct variation equation has no number after the x is a y-intercept, so it's really plus 0, okay? Now, how can you tell it, like with that, I know that that's direct variation, but if you weren't sure, how could you tell? Let's say you're sitting in a science class and you collect some data for some experiment that you're doing in the lab, all right? And your teacher says that, hey, is this direct variation? How would you be able to tell? Well, that's where if you rearrange this equation, you can solve for k. K is equal to y over x, which, by the way, k, the letter k is used because it is considered to be a constant. Like your pay is constantly $8 per hour. That's the constant. What changes is how many hours you work and therefore how much pay you get. But what stays constant is your pay. It's spelled with a k because in German, constant is spelled with a k. And so probably whoever started using a letter to represent the constant probably spoke German, okay? That'd be my guess. But this formula, if you solve for k, it says you can find the k value by taking y divided by x. So if you're sitting in a science class and you are collecting data and you think it might be direct variation, what you would do is take a corresponding x and y value and divide them. Take y divided by x and see what value you get. Then you would take another data point and do the same thing. Now, in math classes, you do that, and k would probably come out to be the same exact value every time. In a science class, you're doing experiments, that's not the way the real world works. So you might, let's say, one time you might come up with 2 for your k value. The next data point you do might be 2.03. The next one might be 1.97, but these should be fairly close to the same value. And then you could say, like, our best fit line, or you guys have probably done it as a linear regression, a regression line. You would then figure out what the k value is. You'd be able to write your equation, okay? So, as I said, the characteristics, first off, is that if you're reading this in a word problem, and we will be doing word problems in here, it might say something like y varies directly as x. Or in the case of your pay, it would be that your pay varies directly as the number of hours you work. So it doesn't have to be x and y. We're just throwing x and y in there because we don't know what situation we're dealing with. Okay. Also, instead, it might say y is directly proportional. That's the whole thing where if you double one, the other value doubles. If you cut one in half, the other one gets cut in half. That's proportionality going on there. All right. Just like you did with similar triangles. You had two similar triangles, they were in proportion to each other. Okay, so it's a kind of similar situation. And as I said, the graph is a line and it passes through 0, 0. Inverse variation, instead of having the variable times the constant, you can see the constant is being divided by the x. So in this case, instead of when you double the x value, instead of the y value doubling, it actually does the opposite. So if you double the x value, the y value gets cut in half. Or you quadruple the x value, the y value would be quadrupled. Okay? And it would look like y varies inversely as x, or y is inversely proportional to x, and so forth. Sorry, I didn't mean to go past that. Now, an example of this, I always think about like if you, whenever I was a kid, and my mom and dad would say, you have to go play outside, you have to stay outside, because my dad would say, I'm not going to air condition the whole neighborhood. And so he'd be like, you're not going in and out. And I'd be like, but I'm thirsty. And he's like, use the garden hose. So I'd go over and I'd turn off on the garden hose, and if you've ever done that, you know that it's good for drinking out of, but it's really slow on like the water pouring out of it, right? And even if you turn it up really high, it's only so much water coming out of there. But I remember like doing that, and then I got this great idea when my sister walked by, and I thought I could squirt her with water. But if you just take the hose and point it at that person, how good is it at soaking them? Not very good, right? Unless they're like right on top of the hose. But if they're like 20, 30 feet away, you're stuck. You can't get them wet unless you do what? You put your thumb over the opening, because here's what happens is that you've got this opening to the hose that has a certain cross-sectional area. So think about like the area of a circle is pi r squared. So right now it has a certain area to it. And the pressure of the water coming out is inversely proportional to the cross-sectional area. When you put your thumb over the opening, what you're doing is making the opening smaller. So you're decreasing the cross-sectional area, which increases the pressure of the water coming out. And then you're able to shoot people from really far away, and you have a good time with that, right? So that's really what is going on there, all right? So that is an example of inverse variation. And there's lots of examples of those things, and we're going to be looking at combining these as well, because sometimes you can have direct variation and inverse variation going on at the same time. Or you can have direct variation not just to x, but to x to like the second power or the third power. And I'm going to show you some examples of that in this section. But before we get to that, what I want you to do is I want you to look at these two situations here. I've given you two XY charts. One of them is direct variation. One of them is inverse variation. And what you need to look at is this information right here. If you think it's direct variation, you should be able to take each point and take its y value divided by its x value, get the same value every time. If you think it is inverse variation, this is the formula you'd use. I didn't mention that, but k is equal to the product of x times y. Again, you can also look at the data and look at it and see, like, make a guess based off of if one is increasing and the other one is increasing at the same time, it's probably direct variation. And if one is increasing and the other one's decreasing at the same time, it is probably inverse variation. So take a look at those and see if you can figure out which one is which, and then also see if you can figure out what the k value is so you can write your equation. So when you look at these two, the first one I suspect is inverse variation, because as x is increasing, going from 5 to 10 to 15 to 20 to 25, the y values are decreasing. So I suspect that it is inverse. But I don't know that for sure until I confirm it by taking k is equal to x times y. So if I do that in each case, 5 times 24 is 120. 10 times 12 is 120. 15 times 8 is 120. Not 128. But I was about ready to sneeze, so my mind went crazy. All right. 20 times 6, 120. 25 times 24 fifths is still 120. So my equation on this one would be y equals 120 over x. That would be my inverse variation equation, so it is indeed inverse variation. The second one, I suspect, is direct variation. Why? Well, my first guess is because as x is increasing, my y values are decreasing. But if it's direct, your k value is found by taking y divided by x. So if I do that in this case, I get 2/5 for the first one. The second one, I get 4 over 10, which reduces to 2/5. The third one, I get 6 over 15, which reduces to 2/5. And the fourth one, I get 8 over 20, you guessed it, reduced to 2/5. So since it's direct variation, my equation is y equals the x value, or the k value, times x. That is my final answer, so it is direct, and that is my equation.